Good morning, everybody. Are you feeling it? Halfway through the semester? Yeah, it's that halfway kind of, I've done so much, I gotta do just as much more. So yeah, I feel it too. I have been summoned to jury duty next week. Maybe. It's that thing where they toy with you, right? Every night you got to check and see if your life is going to be thrown into disarray the next day. And so just keep your eyes peeled for the announcements, right? So like for Monday, I'll know by tomorrow night, right? And I'll post an announcement if I'm going to, I'll cancel lab, right? If I have to go in on Monday. So some of you are like, yes, Monday. Pray for Monday. Tuesday lecture. So I think the only thing that could really sort of affect you guys would be lab on Monday would be the big thing, right? I can recover a lecture anytime, but recovering lab's a bit more difficult. Speaking of which, your lab on Monday is lecture. So I needed more time to lecture on this than was in the schedule, so I'm going to co-opt some of the lab time for lecture, right? So just be ready for that, and if I get called into jury duty, we'll just burn the calendar and figure out what's going on, right? My poor 2A students have an exam next week, and so I think they're all praying to miss the day of the exam, okay? But I told them, I said, I have another teacher, Mr. Evans can come in and give you the exam, that's not a problem, right? But missing the review day and the lab right before the exam, that would be devastating. So. We'll see what happens. They call me in, they find out I'm a physicist, and then they let me go. I wish that they would just put it on my thing, right? No lawyer wants this guy in a courtroom. Anyway. Let's talk polarization, and then we're going to get into optics of mirrors today. So remember, polarization was that thing where light will wiggle in just about any direction, but if it goes through a polarizer, it's going to force it to wiggle in only one direction. And I demonstrated that last time. Here's a few more video demonstrations of stuff that's going on, because there's more than one way to polarize stuff.
We'll use this glass plate, a light source, and a polarizing filter to demonstrate polarization by reflection. If we pass the beam through a polarizing filter onto a screen and rotate the filter, the intensity of the light on the screen does not change. The light beam is not initially polarized.
Right, no change, no polarization.
If we reflect the beam off a pane of glass, rotating the polarizing filter in the beam causes variations in the light intensity on the screen. The reflected beam is polarized.
The only way for that light to get blocked like that is for the light coming off of the glass to be polarized, right? Because then we can take that polarizing filter and kill it. So, what's going on here? When light interacts with a surface, okay, there is the possibility, and I know we haven't really talked about these diagrams yet, so don't panic. We're going to get there, okay? But you have light coming in and bouncing off the surface, the reflection that takes place. Ignore the refraction, okay? At certain angles, it's called the Brewster angle, the light that gets reflected off of that surface becomes horizontally polarized. It's always horizontal because what the light is doing is it comes in and it interacts with the electrons in the material, and the electrons start to wiggle with the light, but the electrons can't wiggle up and down out of the surface. They can only wiggle in the plane of the surface. And so when the light comes back out from those wiggling electrons, it's polarized. Again, this happens at something called the Brewster angle. That angle's darned easy to find. Tangent of the Brewster's angle is equal to a ratio that I'm going to talk about later. So I'm just going to drop that on you. There's this thing called index of refraction. Not that hard, but we got to get past mirrors before we can kind of talk about it. So I'm going to come back to this, right? But I just wanted to point out that polarization can happen in other ways, not just through polarizing filters. This is an absolutely terrible picture. I know this because I took it. And it's not terrible because I took it. I took it on purpose to be terrible. Okay? It's a picture of a driftwood stump on the beach of coastal California, like a redwood that got washed in the water and all that kind of stuff. And you can kind of see the beach sand behind it. You can see the wood here. And you see like this little puddle of water? Okay? And there's nothing in the picture for scale, so it's kind of hard to tell. But do you see how reflective that stump is? Do you see the very, very bright sort of white highlights that are happening on the stump as the sunlight reflects on it? That sunlight that is very bright like that, okay, we call that glare. And if we go outside on a summer's day, the sun's high in the sky, we go out and look at all the cars in the parking lot without our sunglasses on, we'll be like, oh, it's too bright, it's very glaring. There's lots of glinting and bright like reflections coming off of those cars. That's all horizontally polarized light. That's all light that's coming in your eyes, and our eyes are really sensitive to that horizontal polarization. Vertical, not so much. But horizontal polarized light coming at us, we're like, oh, bright! And so that's why polarized sunglasses or polarized lenses in regular glasses are mounted vertically. What are they going to do to that horizontally polarized light? Going to cancel it out. And when you cancel it out, and all I did here, I have a polarizing filter on my camera. I rotated the polarizing filter to cancel out the highlights. And do you see what happened? The picture all of a sudden becomes better, nicer, not as harsh. The colors are warmer, right? Notice the detail that you can start seeing in the wood up there that's kind of lost when we've got all that horizontal, all this glare coming through, right? Okay, this is just a polarizing filter on the lens of my camera, right? And the other thing that you may or may not notice now is, where's the puddle? You can kind of see that there's water there, right? But where did the water go? What color is water? It doesn't have a color. How do you know when water is there? How can you tell that there's water? When light's bouncing off of it, right? We get rid of the bounces, right? It can become very difficult to see something that is clear. Polarization happens in the sky. Molecules of air will get sunlight shown on them, and when they re-emit that light, there's a possibility that that re-emission will end up being in a singular plane, meaning that you will get polarized light. Here's a picture. I didn't take either of these pictures. They're both terrible too. But, because who puts power lines in their pictures? Anyway, do you see how the top picture, you can't see the clouds? Like just everything's kind of blown out and the sky has no detail. And look at the clouds in the bottom picture, right? All of a sudden we can make that out. Oftentimes when we are seeing polarized light in the sky, we say it's like hazy. There's where, yes, this is the San Joaquin Valley in Fresno. It's haze. It's smog, actually, right? But some of that is horizontally polarized light that's hitting you, right? And if you put sunglasses on, it's like, ooh, I can see through the haze. Not really. Okay, you can't see through particles. But it does cut out a lot of that glare. This is a great, I want to be here, right? Things that I like about this picture. There's nobody in it. There's some hills or mountainous things in the distance. It's just nice, right? Okay. But notice what happens when you take the same picture with a polarizing filter. Check out the clouds in the sky. Do you see how they all of a sudden become clearer? Right? Look at the water. You can see below the water almost, right? As we take some of those glares and those highlights out. So In photography, in the art of photography, which is really the art of capturing light, you have various tricks to pull, right? To influence how that light is perceived. Okay? And when we get to cameras and stuff, I'll give you some more insights on how to use the absolutely awful cameras that are sitting in your pockets. Sorry, I just had to get that. Actually, there's an adage in photography, the best camera is the one that you have with you. Just whatever it is, right? Capture the moment. The problem with these cameras, okay, is that the lenses just are too small. Physically, you can't capture light in the same way as you can with a full camera setup. I showed you the computer screen demonstration where I rotated the polarizer in front of the computer screen and how it caused the computer screen to go off, right? That's because these screens have polarizers in them. And a liquid crystal display, an LCD display, is actually the liquid crystal part is little tiny pixels that they can put voltages across. And when you apply a voltage, it causes the crystal to rotate and to polarize the light that's passing through it. And so you can control not just a pixel going on and off, but you can actually control how much light gets through that pixel by changing the plane of polarization. And of course, you need a polarizer in the system to be able to take advantage of this, which is why my polarizer was able to block out the light eventually, right? If I could get the same rotation as those crystals were in that display, then no light gets through. Actually 90 degrees to it. But anyway, LCD displays use polarizers in order to make all that happen. Don't confuse that with LED displays. A light emitting diode is a different kind of thing. Doesn't require a polarizer and requires quantum mechanics. And we'll get there when we get to quantum mechanics. All right. Because yes, you are staring at quantum mechanics every time you look at your phone. Because I don't think there's any phones manufactured in the last like 8 years that use an LCD display. Could be wrong. I haven't checked all of them. Okay. What we're going to do is we are going to go into optics. So this is the implications of Maxwell's equations. Remember, Maxwell discovered that light was a wave, and we have these wave-like things in the electric and magnetic field. The good news is that we are going to cheat a lot, okay? Instead of having to constantly worry about things like sine and cosine functions that describe these waves, it turns out to be easier and very accurate to refer to rays of light. Rays of light they're not vectors. I know this looks like vectors, but don't panic, okay? It's not a vector. It's a line, and that line points in the direction of the propagation of a wave. It very literally is sort of at that cross product between the electric magnetic fields and the direction a wave is going. We draw a ray in the direction that the wave is propagating, and then we sort of get rid of all the wiggles. Because as it turns out, the wiggles are important, and we'll loop back around to them here when we get to interference. But if we want to understand how light interacts with surfaces, how it bounces off things, how it goes into things, really the only thing that matters is the direction it wants to go. It doesn't matter if it's wiggling transversely or all that kind of stuff. And so, although light as a source, right, if that blue ball is light coming out, we technically would draw sort of these bubbles, these wave fronts of light coming off. What we're going to do instead is just draw arrows. And we typically just draw the arrows that are important. So even though there could be a whole lot of light bouncing off of this surface, there's really only one direction that all of that light is heading. So instead of drawing all of them, we're going to draw one of them. And what you're looking at here is a ray diagram. It's a diagram that is giving us something called the law of reflection. when light bounces off of a mirror, shiny surface, okay, whatever angle that light hits the surface at will be exactly the angle it gets reflected at. So if you have light incident at a 45-degree angle, it means that after the bounce, it'll be heading out at 45 degrees. If it's 75 degrees coming in, it's going to be 75 degrees. If it's 5 degrees coming in, it's going to be 5 degrees coming out. That angle in and out is the same. But there's some terminology here and some standards that we need to make sure that we are all on the same page so that we can all be talking about the same thing. First of all, notice in this picture they're using I and F for like initial and final. That's non-standard notation in the world of optics. We usually use incident. The ray that hits the surface is the incident ray. And then we use the reflected ray to talk about the one that bounces off. So I'll do my best to do initial and final, but a lot of times I'm going to screw up, okay? Because it's been drilled into me. It's the incidence ray and then the reflected ray. And then if we're talking about refraction, which we'll get to next chapter, it'll be the incident ray and the refracted ray, right? So just realize, sometimes, a lot of times you'll see me drew like theta 1 and theta 2, okay? That's just the in and out. So I apologize in advance for my loosey-goosey notation on this. I've been through a lot of optical systems in my career, and they all basically mean the same thing, we're just arguing over what symbols we're going to use. More important than any of that, though, do you notice where they are measuring the angle from?
When it hits the mirror.
It's measured from the vertical. So a 0-degree angle, what direction is the light coming if the light is hitting the surface at 0 degrees? Straight down. And if it's 90 degrees, then the light is moving parallel to the surface of the mirror. So just realize that everything in optics is measured from the normal to the surface, a line perpendicular to the surface. Okay? There's various historical and mathematical reasons for that. It actually turns out the math is easier if you do it that way. But and so we're not going to go change any of that. But just watch out. Something that physics textbook authors love to do is make problems harder when they don't need to be. You've heard me complain about this before. And one of the tricks they'll play on you is give you the wrong angle. Right? They'll say something like, oh, the sun is 30 degrees above the horizon, and the sunlight hits the surface of a pool like a mirror, right? Is your angle of incidence 30 degrees? No, what is it? 60. Do you see what kind of, just be careful, right? When you're doing the optics, you need to make sure the angle of incidence is measured from the vertical. All right. Reflection. We'll get to plane mirrors in a second. Let's talk about specular and diffuse reflection. There's different kinds of reflection, two broad categories of reflection. The first one here, okay, is specular reflection. Do you see how that beam is coming off of this surface nice and clean? Whereas that reflection right there, the diffuse reflection, is like, it's like the beam came in and then it's just like going in all directions. Reflection, though simple, right? A beam of light coming into a surface bounces off at exactly the same angle it came in at, right? In and out, all reflection. When you have a surface that's rough or uneven, you're going to get a lot of different angles depending on where you are in that beam of light. And the reason I'm talking to you about this is because you've experienced this if you've ever driven your car at night. The lane lines that are supposed to keep that person on that side of the road and you on this side of the road have a tendency to disappear. You ever experienced that? Driving along and all of a sudden you can't see where the dotted line or the double line is? Here's an example, okay? So this truck's headlights in a parking lot with the water, with the wet surface right here. Do you see how the lines are not really clear? It's because the reflection there on the left-hand side is diffuse. Specular. It's coming out of the headlights and coming straight at you and is probably horizontally polarized too. Okay? And so you're just getting a lot of light hitting you and you're not being able to see the features of the surface. When the reflection becomes diffuse, when the energy of the light's going in all different directions, you can start to pick out surface features. Now, there's something that they try to do to improve safety at night while you're driving when the lane lines disappear. Because they disappear because that water, that film of water that's over the top road surface, and the reflection off the surface of the water is specular, it's very direct. What are the things that they put in the road to help you see where the lane lines are supposed to be? They're little reflectors, those little bumps, right? They're not there to wake you up when you fall asleep driving. Don't do that, right? Those are the rumble strips, okay? Those little reflectors are called retroreflectors. I really should get a picture of one. I keep forgetting to put it in here, okay? But a retroreflector doesn't mean it was installed in the 1970s, okay? A retroreflector means that the light goes in and comes back out in exactly the same direction. If you mount 3 mirrors in a triangular pattern, then after 2 of those bounces, you'll have exactly the same angle in and out. Not going to do all the geometry of that, but it's really, really cool. What it means is that no matter which angle of light hits that reflector, the reflector will always send the light back at where that beam came from. So if your headlights are pointed at one of those retroreflectors, you are going to see the reflection, no matter what angle you happen to be looking at that reflector. A retroreflector always bounces something directly back because there's more than one bounce inside of there, and which makes those things look so bright, okay, when you see them beside the road. So tonight you're driving around, you see a retroreflector, okay? Now, every once in a while there's a blue one. There's white ones and red ones and some yellow ones, but every once in a while there'll be a blue one, and it'll be like right in the middle of the road, not near any of the lane lines. Anybody know what those are for?
Fire hydrant.
Yeah, it's where the fire hydrants are. Okay, so that at night, fire dispatch crews can tell exactly where the hydrants are. You see a blue retroreflector, just look off to the side. Don't take your eyes off the road, don't crash. But there's a fire hydrant somewhere right there. Could be in a bush or something, but yeah, there's a fire hydrant nearby. Okay, plane mirrors. I brought one. Not very big, but okay. So, perfect example of law of reflection. Okay, if you stand in front of the mirror, my alter ego is inside there. Okay. And the light coming off of me, bounces off the mirror, it goes back to my eyes, I can see it, right? Okay? If we take that mirror and we tilt it, right? Now what do you see? You see it, right? Because the light, right? Okay? Angle in equals angle out, okay? What way does a mirror reverse images? When you wake up in the morning and you see glorious you, maybe not so glorious you, depending on your opinion, right? Okay. I think my kids always said I had physics hair in the morning, right? So when you look in there, what do you see? A reflection that is inverted top to bottom, left to right, or front to back? Notice those are the 3 cardinal directions, right? Left to right? Okay, what would a top to bottom reflection look like? You would be upside down, right? And that, not standing on my head this morning, okay? Front to back. Oh, okay, looking at the back of your head. Left to right? What would a left to right reflection look like? Hands are mirrored, or anything pointing to the right would be pointing to the left in the thing. So when you raise your right hand, right, and you see your alter ego in there, your alter ego's hand, what hand went up? Can everybody see the tip of my pen? Probably not. Can everybody see the red tip of this one? Okay. Which way is it pointed? To the right. When I hold it into the mirror, what direction is the reflection pointed? To the right. In order for this to be a left-right reflection, what would the pen have to look like in the mirror? Pointed the other way. Plane mirrors do not reflect left and right. But Mr. Balogh, my right hand. What is this? This is my left hand, right? Okay. What's this? This is my right hand. My left and right hand are mirror images of each other, but not left and right mirror images, and not up to down mirror images. So what's left? Front to back. But isn't front to back supposed to be I can see the back of my head? Pen pointed this way. What end do you see? You see the back end. What end do you see in the mirror? The front end. That is a front to back reflection. Front to back doesn't mean you get to see the back of your head. Okay? What it means is the object that you're seeing, you see the back of it, but in the reflection, you see the front end of it. So mirrors, plane mirrors, reflect front to back, not left and right. We're fooled into thinking it's a left and right reflection because our hands are a front to back reflection along our axis of symmetry. Okay? They're not left to right. It doesn't work. But front to back reflections does work. Which is why we are fooled and why your parents are wrong. They told you, oh, you're looking at your left hand, it's your right hand, left hand. No, it's not. It's still this is still my right hand. It's just I'm looking at a front to back reflection of myself, not a left to right one. So there, you've learned something today, right? Now you can impress people with your knowledge, or not, as the case may be. All right, so we established the direction of reflection. The second thing we have to establish here with what we're seeing in mirrors, okay, is the fact, and I've got to break this to you gently maybe, or maybe I just won't and just tell you straight out, okay? What you are seeing is not real. You okay? Are you all right? You all right? Okay, you all right? Okay. What do I mean by that? When I look in this mirror, and you look in this mirror, right? We see somebody, some things, whatever it is, right? We see them existing where? Like if I stand 1 meter in front of this mirror, where do I see my alter ego? 1 meter on the other side. Where is this image, the image in the mirror, where is it forming? My eyes? Your eyes are just collectors of light, okay? Let me see if I can't help you understand what's going on here. So we've got this projector in here, right? Okay? This projector is creating an image. Where is it creating an image? On the screen, right? Okay? That image is real. It's very real. Your grade matters. No, I'm not that kind. It's actually physically there. And how can I tell if it's actually physically there? Aha! I can interrupt the rays that are coming from that projector and this image right here, right? I can block the real physical rays that are present here. But in this mirror, what's happening? Remember, the law of reflection's happening, right? So the light comes in, the actual physical rays come off of me, hit the surface, and go where? Back. And we see something that's not inside there. My bathroom is on the second story of our house, and it's a second story drop into the backyard on the other side of that wall. When I wake up in the morning, okay, the guy that I know is much more handsome than I am, right, is standing in my backyard hovering, what's going on here? Where does this image form? There is no way you can interrupt anything that's going on inside this virtual reality. So where does this image form? There's only one place that it can form.
Surface of things. In your mind. In your mind.
In your head. What you are seeing in a mirror is called a virtual image. It's virtual because your brain has made it up. Your brain has made it up based on very real physical rays of light that have hit your... I'm not saying it's make-believe or metaphysical or philosophical or political or anything else. What I'm saying is your brain has been tricked. Your brain has seen light bounce off of this mirror, and your brain says, oh, light travels in straight lines. Therefore, I'm going to follow that ray back to its source. The source of that straight line is somewhere back here. But there's nothing there. The difference between a real and a virtual image. A real image, you can interfere with the real physical rays that are present. A virtual image, although manufactured and generated by real light rays, is a figment of your brain's imagination and its evolved ability to follow light back to its source. And it will follow that rule so strictly that it will form an image of something that simply isn't there. Real objects exist. The real you exists. The real rays exist. But what does your brain do? Notice it doesn't follow the bounce off of the mirror. What does it do instead? It follows the rays back and produces a virtual image. We use these terms, virtual and real, to describe the kinds of images that are made upon reflection and refraction and every other optical phenomenon we're going to talk about. So I'm trying to give you a vocabulary for talking about optics. So what are the ways that we can describe an image? So first of all, we can talk about the nature of the reversal. Okay? We call this the image orientation. Okay? It's either upright or inverted. Okay? That could mean a left to right flip or a front to back or a top to bottom. That one's, it's not so much loosey-goosey. You'll see here in a minute that we're going to stick this all in a kind of a one-dimensional plane. Okay? But an image that gets flipped for whatever reason, front to back, left to right, or up and down, we just say it's inverted. Okay? If there's no flip, if the orientation of the object and the image that's being looked at or perceived is the same orientation, then we say it's upright. But if there's any kind of reversal, we say it's and inverted. So is it upright or inverted? Is it real or is it virtual? And the way that you tell, I'll describe later, okay? We're not tools for this. But really the way that you can tell is if it's a real or virtual image is if virtual rays are present, if your eye is following light back to its source and is getting on the other side of the mirror, that's a virtual image, okay? The test for real or virtual is always, can you interfere with it, right? And in this case, I cannot interfere, right? There's nothing I can do on this side of the mirror that's going to get in the way of your perception of this virtual image. All right, third way we have to describe optical phenomenon is whether or not the image is magnified or reduced. So this doesn't happen in your bathroom mirror because it's a flat or plane mirror. The magnification of your bathroom mirror is 1. 1 meaning nothing's happened. You're as tall as you see in the mirror, okay? But if you've ever been to a fun house mirror where there's wiggly, crazy shaped mirrors and all that kind of stuff, sometimes you can look short, sometimes you look tall or thin or wide or whatever, okay? Funny things are going on with magnification there. So a magnification of less than 1 is a reduced image. And a magnification of anything bigger than 1 is a magnified image. And that number that I'm giving you is the power of the magnification. So if the magnification is 2, how much bigger is the image compared to the object? It's twice as big. If the magnification is 10, 10 times as big. Okay? Binoculars give magnifications. If you ever go to buy binoculars, they'll give you the power of the binocular. They'll say it'll be a number times another number, and it might be 8 times 40, or they'll say 8 by 40 binoculars. That first number is the magnification power. What they're saying is things will appear 8 times bigger, or since human brains are weird, 8 times closer, okay, than they would otherwise. The second number is the millimeters of the diameter of the first lens in the binocular. The bigger the lens, more light, clearer image. All right. So that was plane mirrors. We want to talk spherical mirrors now. And this is where things are like, what? I thought mirrors were all just flat things. No, okay. Mirrors come in lots of different shapes and sizes. Okay? And I brought 2 here that are bendy different. Okay? One of these bends in, one of these bends out. Okay? And there's special names for that we'll get to in a second. But let's talk about what a spherical mirror is. And I know you've seen these mirrors before, right? Where have you seen this kind of mirror?
In the store?
Yeah, like in a store or a hospital, okay? Notice, right, what this mirror lets you do. What can we do? We can see around the corner, right? Okay? So in hospitals, that's important. Because if you're running with a patient on a gurney along one hallway, and you've got another hallway at 90 degrees that has another patient running with a gurney, what do you not want to have happen to the patient? Conservation of momentum problem, right? Don't want that, okay? So they put them up in the corners so you can see around corners. Why do they put them in stores? So you can catch the shoplifters. One of these will always be positioned where a security camera is pointed at it, so now the camera can see more of the store. And so that workers can see what's going on down the aisles, okay? So notice that the image that you see in here, so let's describe the image that you see. By the way, this is a convex mirror. It's spherical in its cross-section because, and this is not how they make them, but imagine if this were cut out of a bigger sphere, right? A big, huge sphere, and we sort of lop off a section of it. That's what we mean by spherical mirror. You can have parabolic mirrors, which is like the section of a parabola cut out, okay? You can have hyperbolic mirrors, all the conic sections exist, okay? But when we say a spherical mirror, we mean that basically it's got the same curvature in every direction, and it's as if it was cut out. It literally does have a radius of curvature, okay, that comes from the imaginary sphere it got cut out. But let's talk about the kind of image that you are seeing here. So first of all, let's not do real or virtual yet. We'll get there, okay, right? But is this image upright or inverted? Upright? Why are you saying upright? Because you're facing the right direction. All your heads are this way, and all your feet are this way, right? So this is not an inverted image, is it? Okay. Yeah. What's this? That's inverted, isn't it? You're all standing on your heads? Okay. So an upright image and an inverted image. Okay. Magnified or reduced? It's reduced. Do you appear smaller or bigger? You appear smaller. Okay? We'll get back to that. Okay, so we know it's upright. We know it's reduced. Now, is it real or is it virtual? I love your commitment. Virtual? One of these is real and one of them is virtual. It's so hard to tell because you don't have all the tools yet. This one's real. Okay? It's really hard to tell. We're going to do a whole lab. Well, not the whole lab, but part of a lab. Okay? Not this week, but next week. Not this coming week, but the week after. Okay? Where, because what's happening this Monday in lab, if I'm not in jury duty? Lecture, right? So the lab after that, we're going to put you in situations where you're going to be able to experience directly real and virtual images. And that will help you get a better handle on how to tell the difference between these. Notice one of these is upright and one of them is inverted. Do you see that? This isn't true all the time, but it's true 95% of the time, okay? If the image is inverted, it's a good chance it's real. If an image is upright, there's a good chance it's virtual. You can start with that and then later see if it proves out in the equations and stuff that I'm going to give you. All right. This one right here is called a concave mirror. It's bending the other way. So convex, where it bent out. Concave, where it's like bending in. And I like to think of it as like you have to walk into a cave, right? The cave entrance is yawning open above you. And then convex is the one where you're not walking into a cave. Okay? That's how I remember the difference between those two words. Okay, I'm going to do something shocking to several people in this room. Okay? What I want you to do is look at their reactions as I do this. Yeah? Yeah?
Weakness.
She's there.
Refusing to look?
That's how I look.
Okay, those of you that experienced it, what did you experience? Come on.
Reality.
Reality, okay, right? What did you see? It was greatly magnified. What they saw was their face roughly 2.5 times bigger than it should be. So like, whoa, me! Right? Was it upright or inverted? It was upright. Real or virtual? It was virtual. So here's the real image that all of you can see. Inverted, okay? Probably reduced for most of you. Kind of depends on how close you are to this thing, okay? But when it gets close, you see a greatly magnified, upright, virtual image. Mostly reduced, inverted real, What's the difference?
The distance.
It's the distance that the object is to the mirror. So we got to start talking about how we measure these things, how we draw these things, how we determine distances and all that kind of stuff. But if you are worried that you haven't had the great experience of magnified me, okay? And I mean, I'll be a little bit gender specific here, but ladies, what is this? It's a compact mirror, right? This is, you flip it out, right? And you can see, gentlemen, what is this? Yeah, we don't use these anymore. Shaving mirror. Okay? A shaving mirror is usually mounted on a stand. It's a little bit bigger, right? But it does exactly the same thing as a compact mirror or a makeup mirror does, right? It's curved slightly so that when you get in close enough, you see a greatly magnified version of yourself and you can really get at those hairs, right? So, this one, like I said, the convex one, which we've seen in hospitals and stores and all that kind of stuff, also exists somewhere else. You look in it, well, I hope you look in it every time you try to change a lane.
Just look over your shoulder.
Yeah, don't you just look.
Supposed to look over your shoulder. Yes, you are, and you should, but most people don't. And I'm convinced most people don't even look in what I'm trying to describe right now.
The rear view
Which rear view mirror?
mirror, right?
The passenger side rear view mirror. Not the driver's side. The driver's side does not have one of these mirrors in it. The driver's side has a plain flat mirror, but the passenger side has one of these. Actually, newer cars have like a kind of a weird flat to angle thing. Okay? So, why? Why put one of these mirrors on the passenger side of the car? Blind spot. Okay? So, do I have a picture of it? Oh, I should have gone through all of these examples. So we'll jump to this one right now. Okay? So there's the passenger side mirror. Okay? Notice how this mirror is able to extend the field of view. You can see a lot more of the room in this reflection than you can in this one, right? But what do you trade off for that field of view? Size, position, and relative position of things. Objects in mirror are closer than they appear. Have you seen that warning? Right? Okay, this mirror doesn't have it for some reason, right? But why is that object closer than what it appears to be? It's reduced, right? And so it's not going to move consistently like we usually expect things to move in a linear sense. Things that are far away are going to look really small and look like they're not traveling very fast, and then all of a sudden, that parked car that's behind you is now hitting your bumper. It's because it's not linear. That warning, objects in mirror are closer than they appear, is trying to tell you something's happening. I'm giving you something. This is called paper. Okay? It used to be how we conveyed knowledge to each other, right? Okay? And so I'm going really. Okay? Start sending that out through the room. Everybody needs one of these. Okay? These are going to be the way that we are able to talk to each other through optics. Okay? These are called sign conventions, and I'm going to bring them up here in a minute. By the time that thing makes its way through the room, okay, we're gonna be able to figure out what's going on here. But let's try to start getting some physics, some mathematical modeling, and some conceptual understanding as to just what the heck is going on in these mirrors. Okay, so again, more sort of terminology and the way that we talk about things in optics. There is always going to be something called an optical axis. You can think of it as the x-axis. It's always, we have one dimension really in optics, okay? And it's the principal optical axis. Usually the direction along which an optic is oriented or the light is traveling. Almost always a horizontal line. Even if this thing's mounted vertically, we'll still draw it horizontally because it doesn't matter. There will be a radius of curvature to a spherical mirror. It comes out as a spherical cross-section, so it does have a radius. And we will often call the center of that imaginary sphere the center of curvature. It's often labeled C, sometimes labeled O for like origin, but that changes from place to place. I've almost always seen it labeled as a C, okay? For a concave mirror, notice the shiny side of the mirror is on the same side as the center of curvature. For a concave mirror, the curvature is arcing towards the center. And the shiny side, the side that bounces the light off, is pointing in. But look at that convex mirror diagram over there. That convex mirror, the center of curvature is on the opposite side of the shiny side. By the way, the shiny side is always the side that the light's coming in on. So notice what the difference is in the direction of the reflected ray. Again, we're obeying the law of reflection here. The angle in equals the angle out. It's just on a curved surface, right? The angle of incidence is going to change depending on where you are on that curved surface. So, as light, a parallel light ray, parallel to the principal axis, comes in, a concave mirror is going to bounce it which way? Towards the axis or away from the axis? Towards it. You see how that bounce comes in and it's coming towards the axis? But look at what's going on in that convex mirror. You see how the ray bounces off and heads away from the principal optical axis? So what this is something called a ray diagram. And the activity that you do to make one of these is called ray tracing. And now I'm looking to see how many of you are video gamers. Because I just used a term that the video game industry has been flowing around for the last like 6-7 years. Okay? Ray tracing in games. Before that, it was Pixar and it was Toy Story, the movie Toy Story, the first one, that pioneered the use of ray tracing in their animation technique. Literally, have a light source, have rays come off of that light source, and follow the physics of what that ray does as it interacts with surfaces and materials and all of that kind of stuff. So in Toy Story, they programmed the computers. The artists set up a situation, and then they simulated light sources and how those light sources interacted with the materials to generate every single frame of animation in that movie. They needed ways to predict how the light would interact with certain kinds of plastics, whether the plastic was shiny and reflective or dull and diffuse. And so there was a lot of mathematics and physics and artistry that went in bringing all that together. But if you go look at the original Toy Story, it'll look a little bit flat. It was Shrek, the very first Shrek, that pioneered the next level of ray tracing, which took into account things like fur and hair and surface features. It was easy with toys that generally had a flat, plasticky surface, okay? But as soon as you start getting hair and fur and ogre earwax and whatever, okay, and onions, there's a donkey, you start getting more and more interaction with all the different things, and Shrek represented a leap forward in the ability of computers to do more ray tracing. And nowadays, you get movies where they're using ray tracing all the time. They use subsurface refraction, where they're actually taking into account that light can like penetrate skin and show like veins and other things and musculature. It's really incredible what we're able to simulate now. But it all comes back to this. This is what the computers are doing. They're sending rays in, using the laws of physics to determine how that ray is going to interact, and then seeing what comes out and rendering the camera's view for what's going on. In video games, if you have a video card that supports ray tracing, what they mean there is that that calculation is being done on the video card. And what was unthinkable, Toy Story took something like, I don't remember what it was. Was it 10 hours per frame of rendering time? And there were 30 animation frames per second in that movie. So it took 300 hours to animate 1 second of Toy Story. And now we can do that in a video game at 80 frames per second in real time. It's a good time to be alive. All right, you can combine more than one ray into a diagram. You can see here we've got a couple of rays. Notice these rays, both running parallel to the principal optical axis, right? In a spherical mirror. Parallel rays will always be bent in the concave case towards a singular point. And that singular point is called the focal point. The focal point for a spherical mirror is always half the distance of the radius of curvature. So you can find this focal point if you know the radius of curvature, and you can divide by 2. So if the radius of curvature is 1 meter, what's the focal point? Half a meter. Okay? Also called the focal length, only focal lengths tend to be used in terms of like lenses, but interchangeably with mirrors. Okay? So the reverse is true also. If you put a light source at the focal point and all the light comes off of it, the light that bounces off the mirror is going to do what? Which direction will it be coming out? If parallel rays coming in bounce off the mirror and head to the focal point, then rays coming from the focal point will do what? Bounce parallel to the optical axis. This is how your headlights work. What do headlights do? They cause bright things to come out and illuminate the darkness, right, in front of your car. The bulb in your headlight is sitting at the focal point of a mirror. So that the light that bulb makes heads which direction? Straight out in front of your car, right? With a little bit of they're not using a spherical mirror, they're using a parabolic mirror to pull that one off. But the bulb is sitting right at the focal point. Go away, come on. Okay. What's this? A satellite dish. What does it do? It dishes satellite. Satellites are sending radio signals from space. And this dish collects those rays. By the time they go from the satellite to the Earth, they are moving parallel to the optical axis of that dish. It's a spherical, concave mirror for radio waves. They bounce off. And do you see the sensor for picking up those radio waves? Sitting out there on the end of this boom? Where do you think that sensor is located? It's at the focus, right? This dish is taking those radio waves and focusing them down onto that sensor so that you can get your MTV. And I did date myself. Nobody gets television like this anymore, right? We just stream Netflix. Okay. Why are there two sensors on the end of that mess? One of them is the HD sensor and the other one is the SD sensor. Back in the day when there was a difference between HD and SD, standard definition and high definition. And the dish was designed to be offset slightly in its curvature so that even though all of them were coming parallel, one would get bounced to the HD sensor and the other one would be offset by a certain amount to get to the SD sensor. There are, in order to understand what's going on in an optical system, you really only need 3 rays. These are called the principal rays. Okay? You will not be required to draw any ray diagrams. I just want to tell you that right now. It used to be that we required all of our students to learn how to do ray tracing and make ray diagrams. Well, the internet's made that very obsolete because you can just go and look up every diagram. There's simulations you can run, and I'll show you some of those in lab on Monday. But I want you to understand when you look at the picture what you are seeing, okay? Because in all of these ray tracing diagrams, there's 3 principal rays that are drawn. A ray that heads parallel to the optical axis and bounces through the focal point, one that heads through the focal point and bounces parallel, and then another one that goes in and out of the center of curvature. Why am I showing you all of this? It all comes down to a common language for working one's way through an optical problem involving mirrors. What I've given you so far basically is a standard x-axis, the principal axis, and then a way to talk about the rays that are happening. Now we need to talk about what direction is positive. Because back in 2A it was really important, right, that we specified what our coordinate system was, what we meant by positive and all that sort of stuff. Same thing is true for optics. We standardize on an angle being from the perpendicular, the normal to the surface. But we also define the sense or the sign of distances that are measured within these optical systems. And the piece of paper that I gave you, did everybody get one? Piece of paper I gave you are the standard definitions that everybody in optics obeys. Okay? If you don't go with this, you are on your own. Good luck. Okay? But notice I gave you ones for both mirrors and lenses. We'll get into lenses next chapter. Okay? So let's take a look at these sign conventions, how we apply them to different situations. And I'm going to have you refer to this, the piece of paper that's in front of you. The reason I gave it to you on a piece of paper is because I wanted you to have that physical experience of seeing the conventions right in front of you. Go ahead, take a picture of it, right? Get it on your phone. You're going to want this out in every problem, every lab, every situation. You're going to want to refer to it constantly, okay? Because it is that important to make sure that we are all talking about the same thing. I'll get it. There it is. Now it's on the PDF, okay? So let's do an example. Now, I know this kind of looks scary, doesn't it? It looks like there's a lot going on here. But we can now pull apart. Notice that they're doing the three principal rays, right, in their ray tracing diagram. Again, you don't have to worry about how to draw those. They'll be given to you in any kind of diagram you've got, right? But the object is an arrow. We always draw an arrow. Doesn't matter what the object is. It can be a penguin, it can be a giraffe, tree, whatever it is, right? We just draw an arrow to indicate its orientation. So if you're going to draw me, I'd just be an arrow pointing straight up, because my orientation, my upright orientation would be this way, right? I stand on my feet, not on my head. So the rays come off of that real object, interact with the mirror, and come back. And you see where all three rays spread out, but then they all come back together? You know when you have a real image, when real rays converge. Follow the rays. If those real rays all come back together, the point at which they come back together is exactly the same point as where they left. Since those three rays were drawn from the tip of the object, their convergence point must be the tip of the image that's being formed. And since there are real rays present, what kind of image is it? A real image. Just like this one right here, where I can interrupt the rays and cast a shadow, I could come up here and interrupt those rays and the image wouldn't form, right? Now, are there just three rays that come off of an object? No, there's an infinite number, right? So I could do this all up and down the object, but we don't. We just say, look, we know the object starts at the principal optic axis, so the image must start at the principal optical axis and go to where the convergence happens. This is a real image because real rays are converging. Is it upright or inverted? It's inverted. How can you tell? The object was pointed which way? Up. And which way is the image pointed? Down. This is a real, inverted, and then what's the third way we describe things? Magnification. So is this magnified or reduced? This is magnified. Do you see how the image, the blue arrow, is longer than the orange arrow, the object? You can look at the picture and go, I know it's real, I know it's inverted, and I know it's magnified. So that's all fine and good, Mr. Balogh, in concept, but how do we do this Like with numbers, like if I'm given numbers in a problem, right? I'm not gonna sit there with my ruler and like measure things. Well, the answer is the optics equation. The answer is always math, isn't it? 1 over the focal point is equal to 1 over the distance to the object plus 1 over the distance to the image. Some books and videos and other sources will have a variation of this equation that goes like this. 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. P and Q. I have never been a fan of P and Qs because I cannot mind my P's and Qs. As far in my brain, a P and a Q is more or less the same letter. They just look very much the same, okay? Which is why, and I'm very grateful your author does this, D sub O, distance to the object, right? D sub I, distance to the image. I'm letting you know that if you ever see a P and a Q anywhere, okay, that's what they're talking about. P is object distance, Q is image distance. All right, so that's the equation that we can use to calculate things about this. This is one of 2 or 3, okay? So let me just give you the magnification equation is minus the distance to the image over the distance to the object, which, by the way, is also negative height of image over height of object. This one comes into play every once in a while. Okay. How do we go and calculate things? Let's do a what if. Let's say that the focal length is 15 centimeters, okay? The height of the object is 10 centimeters, and the distance that the object is from the mirror is 40 centimeters. So, object distance. Distance from where the object is to the mirror along the optical axis. By the way, you might hear me refer to the point where the optical axis hits the mirror as the vertex. That's because that's what it is, okay? So it's the distance from the object to the vertex. Image distance would be the distance from the mirror to where the image forms. I drew it down there for clarity, but it's from the vertex to where the image forms. So let's calculate what this image distance should be. We're going to need our sign conventions to help us. So let's start with focal length. Is the focal length of this mirror positive or negative? What does your sign convention sheet tell you? So sign convention sheet, distance to object. I also put P on there in case you ever run across, right, a video or something where they're using P's and Q's. All right? So distance to the object, front and back. Well, what the heck does that mean? The front of a mirror is the shiny side. This picture could have been drawn in reverse, right? We could have just turned this whole picture around and drawn exactly the same thing. Positive and negative doesn't mean left and right. It means front and back. The front side of a mirror is always the side of the mirror that is the shiny side and the side that the object is. I mean, you don't look in mirrors like this, right? The front side of a mirror is the shiny side of the mirror. And so you might be looking at me, Mr. Balogh, why? Why is there a negative sign for the back side of a mirror? An object would never be on the back side of a mirror because then you wouldn't be able to see it anyway. Partially true. Because if you have more than one mirror, the image of one mirror becomes the object for another one. And you can actually have virtual objects. Okay, if your brain is melting, we're not going to do that. We are going to do some multi-lens systems, but we're not going to do multi-mirror systems. Okay, so we'll cross that bridge when we get there. So, according to this, what are we going to put for the sign for distance to the, for focal length? We were talking about focal length. Is the focal point on the front or back side of this mirror? It's on the front, right? You see where the focal point is? It's on the shiny side of the mirror, right? So in other words, a concave mirror has a positive focal length. We'll do convex in a second. Okay, so I know that my focal length is positive 15. I want to get these signs in here. The height of my object is going to be positive, it's pointing up, okay? Distance to object. What does it say about the sign for distance to the object if my object is on the front of my mirror? It's also positive, so positive 40. So now we go and calculate the image distance. It's going to be 1 over di is equal to 1 over f minus 1 over do, which means the distance to the image is going to be the inverse, 1 over f minus 1 over distance, like that. And I'm going fast here because this math isn't hard. 1 over positive 15 minus 1 over positive 40 gets me 24. Because I put centimeters in, I get centimeters out. What happens if they give you a focal length in centimeters but a distance in meters? What are you going to do? Make sure they're both the same. I don't really care which one it is. Typically in optics we use centimeters. But just make sure it's all the same unit, okay? And you'll be safe. Okay, positive 24. So we got positive 24 for the image distance. Look at your conventions. What does that tell you about the image? Where does the image form? If it's a positive image distance, where are we? Front or back? We're on the front side of the mirror. Is that what our diagram says? Yeah, where is it formed on it, right? Okay, all right. So the diagram helps us to check our math. So how do I calculate magnification? Well, magnification minus distance to the image over distance to the object. That's minus 24 over 40. Yeah, equals 24, yeah, negative 0.6. So this drawing is a little bit off. This happens. Negative 0.6 with no units. What's the negative sign mean? Look at your sign convention. It means it's inverted. Is this one inverted?
Yes.
Yes. Okay. Now, the 0.6, what's that supposed to mean?
Reduced.
It's reduced. Now, the drawing here looks like it's magnified, right? That was my fault. I probably should have put in better numbers, okay? This object is inside the center of curvature, okay, which produces magnified images. But you've already experienced what happens when you get the reduced kind, okay? If the object is really far outside, then this will be a reduced image. I apologize, but I should have engineered that one with my example better. Let's see if there's, did I do? Yeah. This one, when I got up close and personal with the person, I'm going to do the calculation next time, okay? But let's just see what's happening here, okay? The ray diagram is showing us that the real rays are diverging from each other. They're following the laws of physics in this ray tracing diagram, but all of those rays which hit your eyes are separating from each other. So your brain is going to follow them back to their source, not realizing that there's a mirror in the way. Do you see those dotted lines? Those are the virtual rays that your brain draws in order to make sense of the real rays that are going into your eye. So your brain follows those rays back to their source. Virtual rays making what kind of image? A virtual image. Upright or inverted. And in this picture, magnified or reduced. Okay? So depending on where you are in front of a concave mirror, it can change what we see. Again, there's the makeup compact. But where the convex mirror is located, right, you're always going to get bounces away from the focal point. So every single image in a convex mirror is going to be what kind of image? It's going to be virtual. It has to be. Mind your signs. I didn't do the example calculations, but they're really easy. You can do all the homework now if you're careful about your signs. For a convex mirror, the focal length is what? Positive or negative? Where is the focal point on this mirror? It's on the back side. The front side's where the objects are. Front side's where the shiny side is, right? Where's the focal length in this one? Back side. Check your signs. Make sure you get the signs of your focal lengths right. Signs of your object distance, and you'll be fine. I will see you on Monday, probably, hopefully. I don't have jury duty.